Okay, so in chapter 21, we're going to learn how to compute Feynman diagrams. And from what you've already seen, computing a Feynman diagram amounts to evaluating an integral, a momentum space integral. So we could also have called this chapter Tricks to Compute Integrals. And maybe I should even say to compute specific types of integrals, because we'll be studying really the integrals that come from Feynman diagrams. Now, the easiest way to illustrate these tricks is by specifically doing an example. So I'm going to choose an example, and it is an example that we're interested in, and we're going to use this result a lot. It's one of the diagrams that appears in the renormalization condition that sets the value of the physical coupling. So let me remind you what the diagram is. It was a contribution, one loop contribution to the 4-point function. So this is what it looked like. And we've got a momentum P1 flowing into this leg. We've got a momentum P2 flowing into that leg. We've got a momentum K flowing in the loop. And if K is flowing into the vertex like this, then flowing out of the vertex has to be K plus P1 plus P2. And I'm just using the momentum space Feynman rules here. So I've assigned momenta to the lines of the Feynman diagram in a way that's consistent with the conservation of energy and momentum. Okay, so let's write down what this integral is. So let's call it I. So I will be equal to, there's two vertices. So we'll have a minus 4 factorial I. We will have a g, z squared, okay? And this will be squared because there's two vertices. What's the symmetry factor? There's no closed lines. Those two vertices are not equivalent. There are no equivalent diagrams. But the two lines in the diagram are equivalent because they both start on the left vertex and end on the right vertex. So there are two equivalent lines. So we need to divide by a 2. Good. Then we have to integrate over the loop momentum. So we'll have an integral d4k over 2 pi to the 4. I am not going to worry about the external lines. They're irrelevant for learning how to do the integral. And for the application that we're interested in, which is to apply to the matching condition, we drop the external lines anyway. So I'm going to drop the external lines. For the first line, we get I, Z inverse, and then we've got k squared minus m squared plus I epsilon. And then for the second line, we've got I, Z inverse, and then we've got K plus, I don't know why I wrote a K1. Let me just correct that. This should be K, okay? Good. This is K plus P1 plus P2 squared minus M squared plus I epsilon. So that's the integral that we want to do. Let's just simplify this a little bit. Well, how many i's do we have? 2 from the factor up front, then 1 from the first line, 1 from the second line. So the i's cancel. Minus times the minus is a plus, so the signs cancel. Then we've got 4 factorial squared, so that's 24 squared over 2. So that's 24 times 12. 10 times 24 is 240. 2 times 24 is 48. 140 plus 48 is 288. So we'll have 288 for the numerical factor. We will have a g squared. And now how about the z's? Well, we've got a z to the 4 up front times a z inverse times a z inverse. So in total, we'll be left with a z squared. Then we've got an integral d4k over 2 pi to the 4. Then we've got 1 over k squared minus m squared plus I epsilon. And we've got k plus p1 plus p2 squared minus m squared plus I epsilon. when you are studying Feynman diagrams, they will often take this form. And what I'm specifically referring to here is that you have an integral over momentum, and then you have a 1 over a product of denominators, okay? So Feynman has formulated a trick to deal with these integrals. So it's actually called Feynman's trick, okay? Let's maybe swap to a different color. So let's go to blue. So Feynman formulated something called Feynman's trick. It actually turns out that it's going to simplify things a lot if we can add the denominators instead of multiplying them. I'm not going to justify that now, but I will justify that soon. So Feynman's trick is an attempt to write a product of denominators in terms of sums of denominators. So let's imagine we've got 1 over a times b. So a could be one denominator, b a second denominator. Feynman showed that you can write this as an integral from 0 to 1 dx, and then we've got 1 over ax plus b times by 1 minus x squared. Okay. This parameter x is called a Feynman parameter. Okay. You can see that the range of the Feynman parameter is only from 0 to 1, and very often you'll be able to do all of the integrations except for the integral of the Feynman parameter, and this is what you'd actually do numerically. Okay, so let's check this. So what check are we going to do? Well, this is actually a straightforward integral to just evaluate and check what is the value of this integral. So if I was to do this integral, what do I get? Well, I get 1 over, so if I've got 1 over something squared, it's a good guess that the integral is just 1 over something, okay? So this could be my first guess for the integral. How do I know whether this guess is correct or not? Well, I could just differentiate it and see if I get back the correct answer. So let's differentiate this. Well, if I differentiate this, I get 1 over that squared. Actually, I get minus 1 over that squared. So the sign is wrong. But then I also need to multiply by the derivative of the denominator with respect to x. And that derivative will be a from the first term minus b from the second. So I can fix both problems by multiplying by 1 over b minus a. And we know if we differentiate this with respect to x, we'll get exactly that integrand sitting in the integral dx integral. So we need to take this, we need to evaluate this between x is equal to 1 and x is equal to 0. So this was easy enough that we could do this integral by inspection. So let's evaluate it between the two limits. So when we plug in x is equal to 1, we just get 1 over a. And when we plug in x is equal to 0, we just get 1 over b. And then we've got this constant of 1 over b minus a multiplying. Now, for the 1 over a minus 1 over b, let's put that over a common denominator of ab. To do that for the first term, we need to multiply by b over b, so we get a b, minus, for the second term, we have to multiply by a over a, so we get b minus a, and 1 over b minus a. So the b minus a cancels with the 1 over b minus a, and we land up with 1 over ab. Good. So we just check the Feynman trick works by explicitly doing the integral. Now, this is a common thing to get products of denominators. What you will not always get is that it'll be a product of just only 2. You might get a product of 3, 4, 8 denominators. In fact, there's a general Feynman trick formula for that. So it generalizes this formula that I've given here, and you'll find that general formula in the notes. You can also look it up. It's well known. It'll be somewhere on the internet. The only thing you need to do if you've got more than one more than two denominators, is that you'll need more than one Feynman parameter. So to apply this to an integral with many denominators, you will need many Feynman parameters. Okay, good. So now let's apply this to our integral. Okay, so what is I equal to? Well, I will be equal to 288 g squared z squared. We will have an integral d4k over 2 pi to the 4. Then we'll have an integral dx from 0 to 1. And then we need to multiply by 1 over ax plus b times by 1 minus x. Now, what is a and what is b? Doesn't matter. Choose as you like. So I've chosen to take a as k plus p1 plus p2 squared minus m squared plus I epsilon. So that's what I've called a, and that gets multiplied by x plus, and then I chose to call b, k squared minus m squared plus I epsilon times by 1 minus x. And this should be squared. Good. Okay, so the first thing that we are going to do is we're going to rewrite this expression that appears in the square bracket and that I've just underlined in red. Okay, so maybe we'll keep working in red. So let's rewrite it down below. So first of all, there's going to be terms that are quadratic in k, terms that are linear in k, and terms that are independent of k. So let's first of all read off those terms that are quadratic in k. So we'll get k squared. From the first term appearing here, we'll get a k squared. That'll come multiplied by x. From the second term, we'll also get a k squared, and that'll come multiplied by 1 minus x plus. Now let's look for the terms that are linear in k. Well, from the 1 minus x term, there's no terms linear in k, so we can restrict ourselves to the term multiplying x, and there we land up with, so there's 2 k dot p1 plus p2 multiplied by x. And I don't think we did anything wrong yet. No, we didn't. And now let's add the terms that are constant, independent of k. So from the first term, from the first bracket, we'll get a p1 plus p2 squared minus m squared plus I epsilon. And all of those terms multiply into x. And then plus from the second bracket, we've got minus m squared plus I epsilon, and this multiplies into 1 minus x. Good. We will continue in a moment.